All right. So ideally you can hear me. And we're going to talk about the kidneys. Assuming all my technology is working here. Let's go. So here's the whole renal system, if you will, which is going to include, I messed that up somehow, the kidneys and assorted structures. Now, of these structures, we're really only caring about the kidneys. The fun kidney-shaped organs there. Because they're doing all the work. Everything else is just a tube or a pouch or whatever. So there's the kidneys. You see them again, slightly protected by the ribs. On either side of the vertebral column. Supported by connective tissue, there's fascia, fat that holds it in place, a fibrous capsule. Here we see them. You see they're retroperitoneal, they're behind the peritoneum there. And just in case, there's, again, kidneys. Take a cross-section of the kidney, you see some specific regions inside. We have an outer region we call the cortex, and an inner region we call the medulla. The medulla is made up of pyramids and columns in between the pyramids. A lobe of the kidney is the pyramid and the cortex here above it. That's a lobe, sorry, that's a lobe, there you go. The tip of each pyramid is called the renal papilla. The renal pelvis is this part. So renal papilla here. Each of these little things right here is called a calyx. These little ones are minor calyces. Minor calyx, and they come together into a major calyx. And all those major calyces come together into the renal pelvis. So major calyces, minor calyces. Once fluid enters this region, it's urine, and it's going to go down the ureter to the bladder. What does the kidney do? Well, it's taking stuff out. It's a filter. The big word there is excretion. Now, as a component of that filter, we're regulating the volume of your blood, right? This urine, the fluid that comes out, is an exudate of blood. It comes from the blood, filtering the blood, like urine. So in that process, we're also regulating the volume of the blood and the chemical composition of the blood. I suppose if you're starving, the kidneys can do some metabolic activities, gluconeogenesis, sorry. And there are hormones released from the kidneys. Those hormones include renin and erythropoietin, which we talked about back with blood. Kidneys are also one part of the manufacture of vitamin D. About a quarter of cardiac output goes through the kidneys every minute. Kidneys actually filter the entire volume of your blood 60 times a day. So they're doing a lot of work. Here we see this blood supply through the kidneys. The big renal artery, which branches into segmental arteries, which branches into interlobar arteries, It's this little arch, which is called the cortical radiate artery. Sorry, excuse me. This is the arcuate artery. These tiny ones are cortical radiate out here. Arcuate artery, cortical radiate, the little spokes coming out. Here is actually the pathway of blood through the kidneys. The working unit of the kidney is the nephron, like 1,000,000 of them for each kidney. And the two major parts of this are the glomerulus, which is kind of this spaghetti ball of capillary, and then the tubule system, or the renal tubule. So here is the nephron. So what's going to happen is blood's going to come in here, the afferent arteriole this way. Pressure is going to push fluid out of the blood into this capsule. What's left of the blood is going to come back into here. We'll talk about what happens to that in just a second. That fluid then gets worked through this system, and what's left becomes urine. So the nephron consists of the glomerulus and the renal tubule. Now the glomerulus is the spaghetti ball of fenestrated capillary. Fenestrated means it's got little tiny holes in it. Outside that, we have these little cells called podocytes. So there's the outer layer of the capsule. Here's the podocyte. So this is what we call the filtration membrane. So in order for something to get from the blood to the urine, it's got to go through this little hole, the fenestration, through this membrane, and then through these little slits. Those little slits are created by podocytes. Now, past this, the fluid will enter what's called the proximal convoluted tubule. The proximal convoluted tubule is made up of cells with lots of microvilli. Remember what microvilli are for? Surface area. Surface area for absorption. Lots of mitochondria. What are mitochondria for? ATP. ATP, in this case, is there to power active transport. So here we see these cells of the proximal convoluted tubule. Past the proximal convoluted tubule, we have what's called the loop of Henle, an ascending and a descending limb. The descending limb is permeable to water. The ascending limb is not. We'll talk about that momentarily. So there's the loop of Henle cells. Past the loop of Henle, we have the distal convoluted tubule. Not sodium microvilli here. This is the last stage of this urine production thing, other than what we call the collecting duct, which is going to deliver urine out to the minor calyces and then the renal pelvis and out. In the collecting duct, again, we have cells that are involved in sort of the fine tuning of urine composition. All right, so again, here's the big nephron picture. Most nephrons are in the cortex, they're cortical nephrons. Some of them are called juxtamedullary. So juxta is across, means they cross into the medulla. They're more important in producing concentrated urine. So there's our cortical nephron, here's our juxtamedullary nephron. This purple thing that you see around, those are capillaries. The glomerulus starts with what's called an afferent arteriole. Afferent means coming in. This input, and then this sort of spaghetti ball of capillary, which is expertly drawn in my illustration. And then output, afferent, efferent, glomerulus in between. Notice that afferent arteriole, it's bigger than the efferent arteriole, which means there's more pressure in between. Off that efferent arteriole, that thing comes around and forms the capillaries that go around the tubule system. They're called paratubular capillaries. Because we've pushed all the fluid out by this point, there's not much pressure in there. The vasa recta, again, around the lubopinilian involved in concentrating urine. Picture again. Lots of pressure here, but resistance will bring it down. This is important because the capillaries in that glomerulus are already under quite a bit of pressure. It's important that we get this resistance here to bring that pressure down so we don't damage those capillaries. So that protects the glomerulus from fluctuations in blood pressure. And the efferent arteriole, it keeps the pressure high enough so the kidneys can do their job. Every nephron gets its own little juxtaglomerular apparatus, which is involved in regulating filtration. There are cells that are called granular cells that release renin in response to changes in blood pressure. Now, we've talked about this before. This kicks off our renin-angiotensin system. So renin causes angiotensinogen to become angiotensin 1. Angiotensin 1, we have this angiotensin converting enzyme becomes angiotensin 2. Angiotensin 2, the mechanisms we've talked about before, blood pressure comes up. The maculodensis cells are chemoreceptors that detect really salt content. And then there are cells called mesangial cells that can let these two areas communicate with one another. So let's talk about big picture, because this is really what I'm concerned with. Big picture, why do you pee? Don't say because you needed to. All right. So, you ever seen the show Hoarders? If you haven't, put this on your things that you need to watch over the pandemic list. There are different versions of this. There's an American version, there's a British version. It's like TLC or something. So the principle here is that there are hoarders. If you're unfamiliar with what a hoarder is, it's someone who never throws anything away. You can see back behind Nigel there. Piles of trash. Sometimes it comes to the extreme. Like sometimes you've got someone and they're like, oh, I hoard money, or piles of awesomeness, stuff like that. And you don't really see a problem. Like, what's the problem with having a house full of gold bars or whatever? I see nothing wrong with that. But then other times they have, shelves that have jars of their own urine in it because they're not going to throw that away. You never know when you're going to need it. Then we have issues. So they'll end up getting buried in their own stuff. So what the premise of the show is, you got these guys, they're hoarders, and social worker, psychologist person comes in to help them sort out their lives and their crap so they can live a normal life. Same principle here. Your blood hoards tons of crap. There's potassium, sodium, nitrogenous waste from the breakdown of proteins. So much stuff in the blood. Some of it you don't need. Some of it can be bad. We need to ditch some of it. It's time to clean up your blood. This lady, psychologist, her job is to help him sort out his life and determine why he's got a bunch of dead cats in the freezer. It sounds funny, like I'm joking. I'm not. He takes them out and pets them on occasion. He has issues. Your kidneys are going to do the same thing. They're going to help you sort this out and deal with your blood and all the dead cats in your blood. So, again, watch the show. The first thing they do is they go in and they're like, okay, we're going to clean up your house. And they start moving everything out, except for the stuff that's too big to move. So, like, they can't move out the washer or the dryer or the refrigerator or the grand piano he didn't even know he had. They move out everything they can, throw it on the sidewalk. This dude should have worn a hazmat suit. And then they sort. This is also the first step of urine formation. You throw out everything. Everything, unless it's too big, will go out of the blood at that glomerulus. So here's our glomerulus, afferent, efferent arteriole. Crap that's in the blood gets pushed out here into the capsular space. The filtration membrane, the actual filter that it's going through, consists of the capillary, the fused membranes, and the slits caused by the podocytes. What can go through? Pretty much everything, unless it's big. The fenestrations keep blood cells in the bloodstream. The basement membrane keeps plasma proteins in the bloodstream. And those little filtration slits help repel big molecules. The rest of it goes out. So here's our filtration. Like I said, the kidneys filter your plasma about 60 times a day. The fluid on this side of the filter is called filtrate. And it's pretty much plasma minus the proteins. Urine is less than 1% of that. So we throw everything out, and 99% of it we're going to move right back into the blood. Again, this is much like the show. For the most part, 99% of the junk gets moved out of their house, and about the same gets moved right back in. They get rid of very little stuff because they're just so attached. You really need 1,000 dolls? Well, I can deal with 900 of them. So, in our steps here, filtration, then reabsorption. We're going to move the good stuff back inside. So, they remove all that guy's crap out of his house. Like, wow, you've got old baseball cards or whatever. Sometimes it's that, or sometimes it's cooler than that. Something actually worthwhile. Like, oh, that's awesome. let's put that back in your house. So that is the reabsorption part of this. Sometimes those people will move stuff back in their house without telling anyone. Like, really? Did you move that back in the house? Can we throw it away now? That is secretion. When you go back and you double check and you throw stuff away. So filtration, reabsorption, secretion. Filtration is passive. It's just driven by pressure. So you're not pumping stuff out, you're just shoving it out. The net filtration pressure we talked about in circulation. Here it's about 10 millimeters of mercury, because the afferent arteriole is bigger than the efferent arteriole. That creates pressure in between here, shoving that fluid out. And now it's out here, and it is, again, filtrate. The GFR is the glomerular filtration rate. Obviously, how much filtrates formed per minute. It reflects how well your kidneys are working, what your kidneys doing. There are two types of mechanisms in play here: an intrinsic mechanism and an extrinsic mechanism. The intrinsic mechanism is just pressure. If your blood pressure is between 80 and 180, intrinsic controls will control it. What this means is that the more blood you force through the kidneys, the more urine you create. Self-regulating. Outside of that, we have extrinsic controls, and the extrinsic controls are hormonal. All right, extrinsic controls: norepinephrine, epinephrine, renin-angiotensin system. And we're not going to get into this again. We've already talked about the effects of angiotensin 2. Raising your blood pressure. Raise your blood pressure, increase filtration. The kidneys are really obsessed with doing their job, is what this amounts to. If there's not enough pressure, the kidneys can't do their job. And if the kidneys can't do their job, they release renin, set off this renin-angiotensin system, raise the blood pressure so they can do their job. I'm not worried about prostaglandin. Moving on. All right, so we shoved everything out. Now we have to get stuff back in. This is reabsorption. All the organic nutrients should be reabsorbed. We pushed stuff out that we wanted to keep, notably glucose. We wanted that. We need that. But we just threw it out. So we need to reabsorb it. We can go through a cell, we can go around the cell. Going around the cell is really limited to ions. Everything else has to go through a cell. But here we see transcellular going through a cell, and then paracellular. Notice that there's both passive and active transport. We're going to reabsorb sodium, usually through primary active transport, and it's going to drive the transport of other things. Very easy to reabsorb sodium. One thing to remember here is that sodium and potassium always go opposite ways. So if you keep sodium, you'll lose potassium, and vice versa. Organic nutrients are reabsorbed by secondary active transport. Here's the thing here. Got this tube, and just for illustration purposes, we've got these transport proteins. Now, each one of these, we can use secondary active transport to move, in this case, let's say glucose. Back over here into the blood. Filtrate. Now, notice that, like in my illustration here, you've got 7 of these little carriers. Each one of them can move 1 molecule of glucose at a time. What that means is that if you put more glucose there than you have transport carriers, then we exceed what's called the transport maximum. The transport maximum is the most of any substance you can reabsorb based on the number of those transport proteins. This is most applicable in somebody who's diabetic. In someone who's diabetic, there's so much glucose here that you saturate these proteins, and then there's no way to get the glucose back into the blood. There's so much of it, you can't pump it all back in. Here in the proximal convoluted tubule, this is the only mechanism we have to reabsorb organic nutrients. If any of those organic nutrients make it past the proximal convoluted tubule, they're in the urine. You can't get them back. So this is why in somebody who's diabetic, one of our big symptoms is glucose in the urine. Now that that glucose is stuck in the filtrate, something else is going to happen. This is a solute. It's dissolved in that fluid. And because it's a solute, dissolved in fluid, it's going to have osmotic properties. And then that glucose acts as an osmotic diuretic. It pulls water toward it in that tubule system. And that's our next symptom of diabetes. They always have to pee, they're constantly having to pee. They're losing fluids and they're dehydrated, so they're constantly thirsty. Water gets reabsorbed by osmosis. It's going to follow those dissolved particles around. So here's another little illustration showing you secondary, primary active transport of stuff in the renal tubule system, especially the proximal convoluted tubule. Proximal convoluted tubule, 65% of sodium and water is reabsorbed. All the organic nutrients, most ions, any small protein that made it through the filter. The proximal convoluted tubule is bulk reabsorption. Everything you threw out, 65% of it is now back in the bloodstream. What's left then enters the loop of Henle. Now the loop of Henle is 2 different things at the same time. It makes this loop that goes down and back up. The descending limb is permeable to water, and the ascending limb is permeable to ions. This creates a mechanism that is self-perpetuating. Those ions, like sodium, come out here, increasing the concentration out here, which pulls water from here, which increases the concentration in here and lets the sodium go out there. And it's just a never-ending cycle because blood vessels immediately remove these products and you never reach equilibrium, so the cycle continues. In the distal convoluted tubule and the collecting duct, reabsorption is regulated by hormones, parathyroid hormone and aldosterone and antidiuretic hormone, the distal convoluted tubule and collecting duct is the last sort of fine tuning that will happen. Aldosterone causes the reabsorption of sodium and the excretion of potassium. Like I said, sodium and potassium always go opposite directions. Secretion, the opposite of reabsorption. This moves stuff from the capillaries into the filtrate, and that gets rid of anything that we don't want specifically, like drug metabolites or things that we accidentally reabsorb, like urea or uric acid. It also helps get rid of potassium. Urine concentration and volume is measured in osmolarity, right? The stuff that's dissolved in water. Normally, urine is very dilute. The kidneys maintain the concentration of the plasma at like 300 milliosmoles, and this is maintained with what's called the countercurrent mechanism. A countercurrent mechanism happens in the loop of Henle when fluid is moving in opposite directions in two segments of the same tube. So here is this. The descending limb is only permeable to water. The ascending limb is not permeable to water at all. It's only permeable to solutes. So here's a great illustration of that. Water comes out on this side. And as the water comes out, it becomes more the filtrate becomes more concentrated down here. And it's so concentrated when it comes back up the ascending part, that salt that's concentrated in there comes out here, which makes the water come out on the other side. And it's a loop. It creates this cycle, and it never reaches equilibrium because blood vessels out here immediately remove those products. So you never get to reach equilibrium. And through this process, we reabsorb more of the water and more of the electrolytes that are in that filtrate. Urea is moving between the collecting ducts in the loop of Henle, and it helps contribute to the osmolarity in the medulla of the kidney, which is going to help you reabsorb water. Here's the vasa recta, which is continuing that osmotic gradient there around the loop of Henle. You're aware that sometimes urine is more dilute than other times. When antidiuretic hormone is not in play, the urine is diluted. When antidiuretic hormone is in play, antidiuretic hormone is going to open channels in this collecting duct, and it's going to let water move back into the blood. With antidiuretic hormone in play, you're going to reabsorb about 99% of the water. A diuretic is something that enhances urinary output. It makes you pee more. There are osmotic diuretics. An osmotic diuretic is just something that's not reabsorbed, like glucose in a diabetic. There are things that inhibit ADH, like alcohol. And then there are things that stop sodium reabsorption. You stop sodium reabsorption, you stop water reabsorption because water follows sodium around. This would be something like caffeine. All right, so segment by segment, here in the proximal convoluted tubule, bulk reabsorption. The loop of Henle We're reabsorbing more sodium and water. We're varying concentration. Distal convoluted tubule, collecting duct, fine tuning, hormonally controlled. Renal clearance is how much of plasma is cleared of something in a time. We can use this to determine glomerular filtration rate, and we can use glomerular filtration rate to determine function of the kidneys. Here's some math that we don't care about. For any substance that's freely filtered and it's not reabsorbed by the kidneys, nor is it secreted by the kidneys, the renal clearance is the same as the glomerular filtration rate. So we can put something in you or even measure something that's already in your blood and then see how quickly it clears the kidneys. You've seen urine. The pigment in urine is called urochrome. This can be altered by different things. Urine, it smells like pee. Slightly acidic, that's important. If it's not slightly acidic, it can lead to the formation of renal calculi or kidney stones. Typically, urine's about 95% water and about 5% stuff. The ureters, the tubes that lead from the kidneys to the bladder, smooth muscle tubes, they look like that. A renal calculus is a kidney stone that forms in the renal pelvis when something crystallizes and then it tries to move through the ureter. It's big enough it can actually block the ureter. Evidently, kidney stones are super painful. And there are different types of kidney stones. Some of them look like sharp little ninja stars. Some of them look like little rocks. If we were in class, I'd pass around the jar of kidney stones that somebody gave me years ago. They're little white stones. And somebody peed them out. So that's disturbing. Past the ureters, we have the bladder, temporary storage for urine. And then the urethra. So there's the bladder, urethra, tube out. We're not going to worry too much about these. All right. So hopefully that will do this for renal stuff.